Today, we're going to prove that the greatest common divisor of a raised to the power of n and b raised to the power of n is the greatest common divisor of a and b raised to the power of n for every positive integer n. To prove this, I'm going to use strong induction. And to use the strong induction, you have to do the following. The first one is to write Pn as a statement with integer n. And number one is to try to prove the base step, which is try to show that P1 is true. Once you have the base step, the next one is to try to prove the inductive step. You have to assume that P of k is true for all integer k, such that k is less than or equal to m, and try to show that P of m is true. If you are not so sure what to do with this m, you may try to show that P1 is true, P2 is true, and P3 is true, P5 is true, or P4 is true, and all the way, and so on. And you may stop at some point. Let's say you stop at P3. Okay? Since all of these P are true, you have to assign that m must be greater than or equal to 3 and try to show that P of m is true. Once Pm is true, P of m, where m is greater than or equal to 3, are all true. So P of 3 is true, P of 4 is true, P of 5, P of 6, and all the way and so on are all true. Now let's get started. So we will let A and B be integers, okay, such that A is not 0 or B is not 0, okay, and we will use the strong induction, okay, or another name of strong induction is the second principle of mathematical induction, and we let P of n to be. I will let P of n be this statement: B, the greatest common divisor of a to the n, b to the n equal the greatest common divisor of a and b raised to the power of n. Okay, let's start with the base step. In the base step, we let n to be 1, right? Then, what do we have? We're gonna have the greatest common divisor of a to the 1, b to the 1, which is the greatest common divisor of a and b, which is the greatest common divisor of a and b raised to the 1. Okay? Then, what do we have? P of 1 will be true, right? P of 1 is going to be true. Okay? Now let's go to inductive step. Take a look at inductive step. Okay, what can we do with this inductive step? So we assume that P of k is true. Okay? Assume that P of k is true for every integer k. Okay? For every integer k, such that k is less than m. And since I just showed that P1 is true, right? So I have to make sure that P of 2, P of 3, P of 4 are all true. So I will assign m to be greater than or equal to 2 and try to show that. P of m is true. Okay, this is what we have right here. So what can we do next? So we try to show that P of m is true, so that we have to use this assumption right here. So by the assumption, what do we have? By the assumption, P of m minus 1 is true, right? Okay. P of m minus 1 is true. That means that we will have the greatest common divisor of m to the minus 1 and Pn and b raised to the m minus 1 equal to the greatest common divisor of a and b raised to the power of m minus 1. Alright, so we try to show that P of m is true. So I want to let D to be the greatest common divisor of a and b. And we will let C to be the greatest common divisor of a to the m and b to the m. And try to show that C equal to D raised to the power of m. Okay? Now to begin this proof, let's take a look at this theorem. Theorem 2.4.1, which state that if you have the greatest common divisor of a and b, let's say which is D, you have integers x and y such that the greatest common divisor of a and b equal ax plus by. Okay? And the one is corollary, which is a corollary 2.4.2. If you have C divide A and C divide B, then C divide the greatest common divisor of A and B. Okay? Now let's go to this proof. Show that C equal the greatest common divisor of C, which is this one, right? Is going to be the greatest common divisor of A and B raised to the power of m. Let's start with this claim. So I gotta show that C divide D raised to the power of m. Let's prove this one. So the first thing we have to do is to use P of m minus 1 here. So the first thing I'm going to do is to let K to be the greatest common divisor of a to the m minus 1 and b to the m minus 1. Okay? And then let's use theorem 2.4.1. Okay? 2.4.1. What is it? So since D is the greatest common divisor of a and b, and K is the greatest common divisor of a to the minus m, b to the m minus 1. Okay? Now, theorem 2.4.1, what does it imply? So it implies that dx is x, y, u, v. Okay, dx is integers x, y, u, v. Such that, what do we have? D, give me a second. D equal to ax plus by. Okay? And what is k? Our k is going to be a to the m minus 1 u plus b to the m minus 1 v. Okay? So this is what we have right here. So this is D and K. So now, what next? Then, what do we have right here? Let's write ax plus by times, times k, right? Times k, this one right here, okay, which is a to the m minus 1 u plus b raised to the m minus 1 v and square and then square. If I didn't have square, what happened? Okay, if I didn't have square, what happened? So because I try to write a to the m time integer, let's say xm plus b to the m ym. I try to have this expression equal d to the m. That's what I'm trying to do. So if I didn't raise to the power of 2, what happened? So let's expand this term. So you're gonna have a to the m xu plus, now a times this one, ab, okay, ab to the m minus 1 v, okay, and plus another one, this term, right, a to the m minus 1 b y u plus b to the m y v. Okay, I forget this x right here. Okay, here. As you can see, these two terms does not have a to the m or b to the m as a factor. Okay, so I have to make sure that all of these term has factor a to the m or b to the m, so that I have to multiply, so I have to raise to the power of 2. Okay, let's continue. So with this one right here is d, right? This term is d. Now what about this term? Take a look at this one here. This term right here is greatest common divisor of a and b raised to the power of what? Of m minus 1, right? Okay, so by P1 or by the assumption, okay, we gotta have the greatest common divisor of a and b raised to the m minus 1. Okay, then what do we have? Raised to the power of 2. Okay, and we gotta have d times d to the m minus 1 square, which is, okay, m to the 2m minus 1, like this. Okay, this is what we have right here. The next thing I'm going to do is to expand the left hand side. Then we gotta have ax plus by. Okay, and what happened next? We gotta have a to the 2m minus 2 u square plus 2a to the m minus 1 b to the m minus 1 u and v plus b raised to the power of 2m minus 2 v square equal to d raised to the power of 2m minus 1. Okay, and expand this term, right? So we gotta have a to the 2m minus 1 x u square plus, okay, 2a to the m b to the m minus 1 x u v, and plus a b to the 2m minus 2 x v square. And next one, okay, expand these terms. So we gotta have a to the 2m minus 2 b y u square plus a to the m raised to the power of, okay, a raised to the power m minus 1 b to the m y u v plus b to the 2m minus 1 y v square. Okay, equal to d raised to the power of 2m minus 1. And as we can see, all this term has factor of a to the m or b to the m. Now take a look at this term right here. It has factor of a to the m, right? And this factor have and this term has factor as has b to the m as a factor. Okay. Then this is what we have. We gotta how do I say it? We're gonna let the term with factor a to the m, okay, plus a to the 2m minus 2 byu squared plus the term with factor b to the m. We can have ab raised to the power of 2m minus 2 xv squared plus 2a to the m minus 1 b to the m yuv plus b to the 2m minus 1 yv squared. Okay, we now have this term, right? And factorize am on the first three terms. We're gonna have a to the m minus 1 x u squared plus a b to the m minus 1 x u v plus a to the m minus 2 b y u squared plus b to the m, right? A b m minus 2 x v squared plus 2a to the m minus 1 b, okay, b to the m is factorized, right? Times yuv plus b to the m minus 1 yv squared equal d raised to the power of 2m minus 1. Okay, great. The problem is we have this term right here, a to the m minus 2 in b, and a times m to the time b to the m minus 2. Okay, because I'm trying to factorize d to the m minus 1, all of these two terms, and I want to divide this equation by d to the m minus 1. So I gotta leave this as equation 1. Now we have that d is the greatest common divisor of a and b. Okay, so since d is the greatest common divisor of a and b, now what happened? We could have d divide a and d divide b, right? Okay, now what happens next? So what do we have is we use divisibility, right? Okay, so dx's integers q1 and q2 such that a equal to q1d and b equal to q2d. Okay, now what happened to 1? Hence equation 1 becomes, okay, what does it becomes? It becomes a to the m, okay, q1d raised to the m minus 1 xu squared plus 2 q2d raised to the m minus 1 xuv plus, okay, what about this one right here? We multiply q1d raised to the m minus 2 and q2d yu squared, okay, plus b to the m. What is a? A is q1d, and what is b is q2d raised to the m minus 2 xv squared plus what is a? Our a is q1d raised to the power of m minus 1 yuv plus Q2D, right? This term right here becomes Q2D raised to the power of m minus 1 yv squared, and equal to d to the 2m minus 1. Okay, so let's deal with this, right? Take a look at this term. What happened? We're gonna have a to the m q1 raised to the m minus 1 d to the m minus 1. Okay, what next? Xu squared plus 2 q2 m minus 1 d m to the minus 1, right? Xuv plus, okay, combine these terms with this one, have m to the raised to the power of minus 2. This is d to the 1. We're gonna have q1 m raised to the m minus 2 q2 d to the m minus 1 yu square plus b to the m, okay, q1 q2 raised to the power m minus 2 and d to the m minus 1 xv square plus 2q1 m to the minus 1 d to the m minus 1 yuv plus, okay, q2 m to the minus 1 d to the m minus 1 yv square equal d to the 2m minus 1. Okay, great. This is what we have right here. And I will divide both sides by d to the d to the m minus 1. Okay, let's divide both sides. Okay, let me write something. So we gotta have a to the m d to the m minus 1 q1 m to the minus 1 xu square plus 2q2 m minus 1 xuv plus m1 raised to the m minus 2 q2 yu square plus, okay, this term b to the m, right? And factorize d to the power of m minus 1, okay, times q1 q2 m to the minus 2 xv square plus 2q1 m to the minus 1 yuv plus q2 m to the minus 1 yv square equal d raised to the power of 2m minus 1. Okay, and we divide both sides by d raised to the power of m, right? Okay, dividing both sides by d raised to the power of m minus 1. So what do we have? So we gotta have a to the m, right? This d will be gone. So I gotta copy this term, and we're gonna have a to the m times these integers plus b to the m times this term, then it equal to d raised to the power of 2m minus 1. Oh, sorry, we have to subtract it by m to the minus 1, right? Then you're gonna have just d to the m. Okay, it's just going to be d to the m. Then what next? What can we do next? Okay, the next thing I'm going to do is to take a look at this c right here. This c. Okay, since c is the greatest common divisor of a to the m and b to the m, what do we have? Since c is this greatest common divisor, that means that c divide a to the m and c divide b to the m. Okay. So what happened if C divide both A to the M and B to the M according to property of divisibility, which is okay by theorem 2.3.1 in the last property, it implies that for all integer x1 y1, C divide A to the M x1 plus B to the M y1. Okay, this is what we have right now, right? This is our C. So C divide this term, and x1 and x2, x1 and y1 is any integers, okay? And take a look at this right here. These are all integers, right? Okay, I gotta write since. I gotta call it u1 equal to this term right here. This term right here. Okay, this is an integer, right? And this term right here is also an integer. Okay, we call it u2, which is this term right here. Okay, this is an integer, right? This is an integer. Okay, so since these two terms are all integers, this term is integer, this term is integer. Okay, so I just write it in u1 and u2. That means that we can plug in this big integer here and here into x1 and y1. That means that we're gonna have C divide A to the M u1 plus B to the M y1. Okay, since now this term becomes u1, right? And this term becomes u2. Okay, A to the M u1 plus B to the M u2 equal D to the M. So this term right here must be D to the M. Therefore, what do we have? And hence, we're going to have C divide D to the M. So we have just proved this claim already. Okay? Wow, it's quite complicated to prove this claim. So let's go to next page. Now, let's do another claim. Claim that, or show that, D to the M divide C. Okay. Okay. Take a look at D, right? So since D is the greatest common divisor of A and B, so what do we have? We gotta have D divide A and D divide B. Okay. Hence, what do we have? We gotta have D to the M divide A to the M and D to the M divide B to the M. Okay, what next? Since we have D to the M divide A to the M and D to the M divide B to the M, what happens? We gotta have D to the M divide the greatest common divisor of A to the M and B to the M, right? Then what do we have? That means that D to the M divide C. That's it. Because C is what? It is the greatest common divisor of A to the M and B to the M. Okay. Now what next? What next? Since we have this one right here and this one right here. So since C divide D to the M and D to the m divide c. So what do we have? We're gonna have c equal d to the power of m. Okay, and hence what do we have? We're gonna have c. Okay, c is a to the m and b to the m, right? The greatest common divisor of a to the m and b to the m equal the greatest common divisor of a and b raised to the power of m. Okay, so hence p of m is true. Okay, so p of m is true, right? So by induction, okay, by strong induction, what do we have? So we have proved that. So we have proved that if, oh, sorry. So we have proved that a to the n, sorry, the greatest common divisor of a to the n and b to the n equal the greatest common divisor of a and b raised to the power of n for every positive integer n. Okay, that's the proof of this problem. So we have shown that the greatest common divisor of a to the n and b to the n equal the greatest common divisor of a and b raised to the power of n for every positive integer n by using strong induction. Okay, so that's it for this proof, and see you in the next video.